A signal is referred to in communication systems, signal processing, and electrical engineering, is a function that conveys information about the behavior or attributes of some phenomenon in the physical world. Any quantity exhibiting variation in time or variation in space is potentially a signal that might provide information on the status of a physical system, or convey a message between observers, among other possibilities. The IEEE Transactions on Signal Processing states that the term signal includes audio, video, speech, image, communication, geophysical, sonar, radar, medical and musical signals. Other examples of signals are the output of a thermocouple, which conveys temperature information, and the output of a pH meter, which conveys acidity information. For example, a microphone converts an acoustic signal to a voltage waveform, and a speaker does the reverse. The formal study of the information content of signals is the field of information theory. The information in a signal is usually accompanied by noise. The term noise usually means an undesirable random disturbance, but is often extended to include unwanted signals conflicting with the desired signal. The prevention of noise is covered in part under the heading of signal integrity. The separation of desired signals from a background is the field of signal recovery, one branch of which is estimation theory, a probabilistic approach to suppressing random disturbances. Engineering disciplines such as electrical engineering have led the way in the design, study, and implementation of systems involving transmission, storage, and manipulation of information. In the latter half of the 20th century, electrical engineering itself separated into several disciplines, specializing in the design and analysis of systems that manipulate physical signals, electronic engineering and computer engineering as examples, while design engineering developed to deal with functional design of man-machine interfaces. Definitions specific to subfields are common. For example, in information theory, a signal is a codified message, that is, the sequence of states in a communication channel that encodes a message. In the context of signal processing, arbitrary binary data streams are not considered as signals, but only analog and digital signals that are representations of analog physical quantities. In a communication system, a transmitter encodes a message into a signal, which is carried to a receiver by the communications channel. For example, the words, "Mary had a little lamb," might be the message spoken into a telephone. The telephone transmitter converts the sounds into an electrical voltage signal. The signal is transmitted to the receiving telephone by wires. At the receiver it is reconverted into sounds. In telephone networks, signaling, for example common channel signaling, refers to phone number and other digital control information rather than the actual voice signal. Signals can be categorized in various ways. The most common distinction is between discrete and continuous spaces that the functions are defined over. For example, discrete and continuous time domains. Discrete time signals are often referred to as time series in other fields. Continuous time signals are often referred to as continuous signals even when the signal functions are not continuous. An example is a square wave signal. A second important distinction is between discrete valued and continuous valued. Digital signals are sometimes defined as discrete valued sequences of quantified values that may or may not be derived from an underlying continuous valued physical process. In other contexts, digital signals are defined as the continuous time waveform signals in a digital system, representing a bit stream. In the first case, a signal that is generated by means of a digital modulation method is considered as converted to an analog signal, while it is considered as a digital signal in the second case. Another important property of a signal is its entropy or information content. Analog and digital signals. Two main types of signals encountered in practice are analog and digital. The figure shows a digital signal that results from approximating an analog signal by its values at particular time instants. Digital signals are quantized, while analog signals are continuous. Digital signals often arise via sampling of analog signals, for example, a continually fluctuating voltage on a line that can be digitized by an analog-to-digital converter circuit, wherein the circuit will read the voltage level on the line, say, every 50 microseconds and employing a fixed number of bits. The resulting stream of numbers is stored as digital data on a discrete time and quantized amplitude signal. Computers and other digital devices are restricted to discrete time. Time discretization. One of the fundamental distinctions between different types of signals is between continuous and discrete time. In the mathematical abstraction, the domain of a continuous time signal is the set of real numbers, whereas the domain of a discrete time signal is the set of integers. What these integers represent depends on the nature of the signal. Most often it is time. If for a signal, the quantities are defined only on a discrete set of times, we call it a discrete time signal. A simple source for a discrete time signal is the sampling of a continuous signal, approximating the signal by a sequence of its values at particular time instants. A discrete time real signal can be seen as a function from the set of integers to the set of real numbers. A continuous time real signal is any real-valued function which is defined at every time t in an interval, most commonly an infinite interval. Amplitude quantization. If a signal is to be represented as a sequence of numbers, it is impossible to maintain arbitrarily high precision. Each number in the sequence must have a finite number of digits. As a result, the values of such a signal are restricted to belong to a finite set. In other words, it is quantized. Quantization is the process of converting a continuous analog audio signal to a digital signal with discrete numerical values. Examples of signals. Signals in nature can be converted to electronic signals by various sensors. Some examples are motion. The motion of an object can be considered to be a signal, and can be monitored by various sensors to provide electrical signals. For example, radar can provide an electromagnetic signal for following aircraft motion. A motion signal is one-dimensional, and the range is generally three-dimensional. Position is thus a three-vector signal. Position and orientation of a rigid body is a six-vector signal. Orientation signals can be generated using a gyroscope. Sound. Since a sound is a vibration of a medium, a sound signal associates a pressure value to every value of time and three space coordinates. A sound signal is converted to an electrical signal by a microphone, generating a voltage signal as an analog of the sound signal, making the sound signal available for further signal processing. Sound signals can be sampled at a discrete set of time points. For example, compact discs contain discrete signals representing sound, recorded at 44,100 samples per second. Each sample contains data for a left and right channel, which may be considered to be a two-vector signal. The CD encoding is converted to an electrical signal by reading the information with a laser, converting the sound signal to an optical signal. Images. A picture or image consists of a brightness or color signal, a function of a two-dimensional location. The object's appearance is presented as an emitted or reflected electromagnetic wave, one form of electronic signal. It can be converted to voltage or current waveforms using devices such as the charge-coupled device. A 2D image can have a continuous spatial domain, as in a traditional photograph or painting, or the image can be discretized in space, as in a raster-scanned digital image. Videos. A video signal is a sequence of images. A point in a video is identified by its two-dimensional position and by the time at which it occurs. So a video signal has a three-dimensional domain. Analog video has one continuous domain dimension and two discrete dimensions. Biological membrane potentials. The value of the signal is an electric potential. The domain is more difficult to establish. Some cells or organelles have the same membrane potential throughout. Neurons generally have different potentials at different points. These signals have very low energies. but are enough to make nervous systems work. They can be measured in aggregate by the techniques of electrophysiology. Signal processing. A typical role for signals is in signal processing. A common example is signal transmission between different locations. The embodiment of a signal in electrical form is made by a transducer that converts the signal from its original form to a waveform expressed as a current or a voltage, or an electromagnetic waveform, for example, an optical signal or radio transmission. Once expressed as an electronic signal, the signal is available for further processing by electrical devices such as electronic amplifiers and electronic filters, and can be transmitted to a remote location by electronic transmitters and received using electronic receivers. Signals and systems. In electrical engineering programs, a class and field of study known as signals and systems is often seen as the cut class for e-careers, and is dreaded by some students as such. Depending on the school, undergraduate students generally take the class as juniors or seniors, normally depending on the number and level of previous linear algebra and differential equation classes they have taken. The field studies input and output signals, and the mathematical representations between them known as systems, in 4 domains: time, frequency, S and Z. Since signals and systems are both studied in these 4 domains, there are 8 major divisions of study. As an example, when working with continuous time signals, one might transform from the time domain to a frequency or S domain, or from discrete time to frequency or Z domains. Systems also can be transformed between these domains like signals, with continuous to S and discrete to Z. Although S&S falls under and includes all the topics covered in this article, as well as analog signal processing and digital signal processing, it actually is a subset of the field of mathematical modeling. The field goes back to RF over a century ago, when it was all analog, and generally continuous. Today, software has taken the place of much of the analog circuitry design and analysis, and even continuous signals are now generally processed digitally. Ironically, digital signals also processed continuously in a sense, with the software doing calculations between discrete signal breaths to prepare for the next input, transform, output event. In past e-curricular S&S, as it is often called, involved circuit analysis and design via mathematical modeling and some numerical methods, and was updated several decades ago with dynamical systems tools including differential equations, and recently, Lagrangians. The difficulty of the field at that time included the fact that not only mathematical modeling, circuits, signals and complex systems were being modeled, but physics as well, and a deep knowledge of electrical topics also was involved and required. Today, the field has become even more daunting and complex with the addition of circuit, systems and signal analysis and design languages and software, from MATLAB and Simulink to NumPy, VHDL, PSpice, Verilog and even assembly language. Students are expected to understand the tools as well as the mathematics, physics, circuit analysis, and transformations between the 8 domains. Because mechanical engineering topics like friction, dampening etc. have very close analogies in signal science, many of the tools originally used in ME transformations have now been applied to signals, circuits, systems and the components, analysis and design in E. Dynamical systems that involve noise, filtering and other random or chaotic attractors and repellers have now placed stochastic sciences and statistics between the more deterministic, discrete and continuous functions in the field. Taxonomists are still not decided where S&S falls within the whole field of signal processing versus circuit analysis and mathematical modeling. But the common link of the topics that are covered in the course of study has brightened boundaries with dozens of books, journals, etc., called Signals and Systems, and used as text and test prep for the EE, as well as, recently, computer engineering exams. The HSU general reference given below is a good example, with a new edition scheduled for late 2013, early 2014.